So, good afternoon and welcome to this presentation. My name is Kleanthis Papagadzopoulos from CAST, and today I will speak about one of the primary components of our TCP/IP core, which is the Content-Addressable Memory. The design of the proposed CAM is based on Cuckoo hash algorithm. And this is a relatively new high-performance scene for hash tables. We will introduce a purely digital hardware architecture that is tailored for FPGA and ASIC implementations. So, CAMs are specialized circuits used to realize a lookup function. In these blocks, the input is stored in an array of stored data, and the accompanying data are retrieved. Hereafter, we refer to the input search data as key, and the relevant accompanying data as value, forming a key-value pair. The primary applications of CAMs is in network devices. For example, in a router, a data packet is forwarded from an incoming port to an outgoing port using a lookup function. Applications also involve LZ compression, image coding, and neural networks. CAMs can rely on hash table techniques, and one that received a lot of attention is Cuckoo hash algorithm. Its attractive features include memory efficiency, constant lookup time when searching for a key-value pair, and a relatively small number of collisions with respect to prior approaches. We focus on the functionalities of CAMs in CAST TCP/IP core. This core supports mainly the TCP and IP protocols, and optionally secondary protocols such as UDP, ICMP, and IGMP. Conventional TCP/IP cores manage multiple sessions by instantiating a primitive building block multiple times, one block for each session. Here, we use a different approach, and we employ an architecture that scales sublinearly to the number of sessions. Specifically, we employ IDs to distinguish sessions, and every time a packet for a session arrives, the session context is retrieved from the memory. This mapping from socket identifiers in an incoming packet to session IDs is realized by the session CAM. And this search process is of high priority and should be performed with high throughput every time a packet for a session arrives. Subsequently, the session context, the session ID is used as an address to access the session context from the memory. There is also a low priority process during connection establishment and tear down, where session IDs are either saved or erased from the session CAM. So the challenge we deal with here is that conventional CAM designs with a few thousand of stored key-value pairs are memory demanding. Typically, for a small number of sessions, a CAM that uses only registers is employed, and this architecture can only be extended up to 8 to 16 key-value pairs or session IDs. The second architecture relies on RAMs and uses directly the input key as an address to access the memory blocks. However, this architecture also presents scalability issues when the number of sessions increases to a few thousand. To tackle this, we adopt a hash-based scene. In general, the main drawback of hash-based approaches is collisions, where two or more keys are mapped to the same memory location. The Cuckoo hash SIM presents attractive characteristics in this context, reducing collision rates. So let's start from the beginning and see how the original Cuckoo hash algorithm works. The main difference of this algorithm with prior approaches is that it deploys multiple hash tables. During the insertion process, the algorithm allows key-value pairs to move to alternative locations in different hash tables to free space for another key-value pair. And this is a measure to resolve collisions compared to prior approaches that employ only one hash function and movements of elements are not permitted. In all hash-based approaches, the input key is used as input to a hash function, and the derived hash is used as an address to access the corresponding hash table. And through this example, we see how the original algorithm handles collisions. Let's say that we want to insert the key S in the hash table. We derive the two hashes and check the corresponding memory slots. Here, both slots are occupied, so we select to evict one element, here the key G, and place S in its position. In the next iteration of the insertion process, we check the alternative slot where G can be stored. Continuing this process, we expect that after some number of kick out and insertion iterations, we will be able to store all key-value pairs in the hash tables. And here it takes exactly 2 iterations to resolve all collisions. And regarding queries, every time we have to look for the value of a key, we have to make exactly 2 memory accesses. The greatest drawback of this algorithm appears to be safe failures. During the insertion process, there is possibility that we cannot store a new key-value pair in the hash tables due to the consecutive collisions. And here we see that during the kick-out and reinsertion process, we reach the initial state where the initial key is kicked out, essentially forming a loop. However, there is no guarantee that we are going to reach this situation after a predefined number of kick-out and reinsertion iterations, or this loop will involve the initial key-value pair. And this is translated to an unbounded latency for hardware implementations. The standard response to this difficulty from an algorithmic perspective is to evict all elements from the hash tables and repeat the insertion process using different hash functions. Of course, the process of rehashing is very costly for hardware implementations, and we completely avoid this technique in the proposed architecture. So, current approaches for Cuckoo hash SIMs fail to provide hardware-oriented solutions on how deadlock situations are identified and the safe abort is declared. Here, the algorithm describes the steps executed during the safe process. The employed approach tracks the number of kickouts and reinsertions and limit this number in order to provide an upper bounded latency for the safe command. The proposed variation is described by the particular example. According to this, if the number of kick-out and reinsertions reaches a threshold of 4 iterations, the steps are reversed and kick-outs are performed in the backward direction. This allows us to reach the initial key and declare a save abort with an upper bounded latency. And this mechanism is called backward reinsertion mechanism. One critical part of CAM design is the selection of hash functions. Most theoretical approaches assume a static set of key value pairs based on which perfect hash functions are derived. For hardware implementations, we are mostly interested in non-cryptographic hash functions that have a small area and relatively low latency. We also consider characteristics such as good scalability when the width of the input key increases, and no correlation between the input key and the output hash value. And two hash functions that demonstrate good characteristics in this context are the Murmur hash and Jenkins hash functions. These functions are built by repeating a number of randomization blocks, the number of which depends on the width of the input key. The Murmur hash function involves the operations with the greatest complexity, having 32-bit multiplications with constants that can be directly mapped to DSP building blocks. Here we also evaluate the resources occupied by these two blocks as the width of the input key increases for an AMD Kintex ultra-scale plus device. And we can see that even for relatively large key width configurations, the resources occupied by these two blocks are less than 2% of the available resources. In the design units, the number of pipeline stages can be configured also at design time by parameters, and this way we take advantage of the pipeline opportunities provided by the DSP building blocks. So let's see in more detail the proposed architecture. As search commands have the highest priority in the context of our TCP/IP core, and save commands can potentially take multiple cycles to finish, we employ two input interfaces, one for search commands and the second one for save and erase commands. Similarly, we have two interfaces at the output, and all the supported commands pass through the same functional units. In more detail, the arbiter selects which command will enter the data path. The hash unit takes the key of the current command and produces the hashes. The next unit contains the memory control logic and the memory blocks that correspond to the hash tables. The search unit checks if the red positions have an empty slot or contain the sought key depending on the executed command. The execution unit selects which hash table to be updated and produces the right enable and the right data signals. In parallel, the reinsertion unit selects a key value pair to be reinserted in case of a save command. Essentially, it produces a reinsertion operation that enters again the data path through this loop. And such a pipelined architecture introduces certain data dependencies between commands that coexist in the data path. 3 types of dependencies can emerge. And in all of these, a search command follows a save and erase or a reinsertion command, and all of these commands share the same key. To resolve these types of dependencies, the architecture contains data hazard registers and related logic that recognizes these situations and forwards the right value to the appropriate unit. And here is the architecture around the hash tables. Each hash table is mapped to a separate 2-port memory block. And this way, the two hash tables can be accessed in parallel. We also employ a set of techniques in order to decrease the number of collisions. The first technique is that we employ multiple slots per memory position. This allows us to search for multiple empty points per memory access before concluding that a reinsertion operation is needed. The second technique is that we allocate more memory space than the minimum required. This essentially increases the width of the output hashes that are used as addresses for the memory blocks in order to increase randomization and reduce collision rates. Initially, we demonstrate the FPGA implementation results for the introduced CAM. From the table at the right, we can see how the critical path scales, the latency of the critical path scales as the width of the input key increases. And this ranges from 2.3 to 3.4 nanoseconds for the greatest configuration that includes a key of 160 bits. For the smallest configuration, the CAM occupies almost 5,100 lookup tables, 8 blockrams, and 18 DSP blocks. A relatively small configuration was also used to derive ASIC synthesis results for the introduced CAM. The synthesis was performed with Cadence Genus, targeting a 7 nanometer TSMC technology node and the 500 MHz frequency. Here the memory blocks are excluded from synthesis as they are usually mapped to memory macro blocks. And the timing report indicates that the critical path lies in the hash unit and specifically in the last randomization stage of the Jenkins unit. Here we refer to the FPGA implementation results for the session CAM and the three examined architectures, the register-based, the RAM-based, and the introduced Cuckoo hash-based, with respect to the TCP IP core resources. We see how the lookup table block RAM and flip-flop ratios scale as the number of supported sockets increases. And in absolute numbers, the introduced Cuckoo hash-based architecture achieves to reduce lookup tables by 73%, block RAMs by 68%, and flip-flops by 72% with respect to the second examined RAM-based architecture. And the previous numbers are clarified when looking the floor plan after place routing the TCP IP core for two socket configurations. The yellow parts denote the resources occupied by the session CAM for the three architectures. The Cuckoo hash-based architecture it provides greater area benefits as the number of supported sockets by the core increases. And the introduced CAM has been also hardware tested as part of TCP/IP core. The picture depicts the testing setup in which an AMD Korea KR260 evaluation port was used. The test includes two TCP/IP endpoints that establish a connection, exchange data, manage retransmissions and acknowledges, and gracefully close this connection. The one end of the connection is implemented in the FPGA using CAS TCP/IP core, and the other end is implemented in the laptop by an application. And the connection is realized through an optical wire that tends to do SFP plus transceivers. To summarize, this presentation introduces a CAM architecture that relies on Cuckoo hashing. And this is a multiple choice hashing scheme that presents attractive algorithmic characteristics that are also translated into good implementation features. The introduced design limits the latency of the save command by using the introduced backward reinsertion mechanism. From the synthesis results, it is shown that the introduced architecture effectively reduces memory and logic requirements, especially for large configurations, compared to conventional architectures. And the proposed architecture can also be naturally extended to different variations that include different hash functions, more slots per memory position, and more hash tables, and possibly an extra amount of memory, like a stash, to further reduce collisions. So I want to thank you for your attention, and we can continue with your questions and the relevant discussion.